Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. Welcome to this video on semiconductor device graphical data presented as VI characteristics. In semiconductor device data sheet, graphical parameters are presented, which helps the designer to assess its circuit behavior. The graphical data presents parameters like electrical operating parameters, maximum ratings, frequency and timing parameters, safe operating area, etc. Graphical data can be used to evaluate dynamic parameters and thereby assess device suitability for a specific application. The polarity and magnitude of the applied voltage determines the device conductivity. Forward or reverse polarity biasing of a semiconductor device determines its conduction characteristics. Thus, extracted data is graphically presented through first and third quadrant graph. The forward bias extracted data from test setup shown is plotted as first quadrant graph. Reverse biasing is the process of reversing the previously applied bias polarity. Reverse bias data extracted from the setup shown is plotted as third quadrant graph. The figure shows typical resistors VI characteristics. The graph slope is computed as the ratio of change in voltage to current and is inversely proportional to the resistance value. That is, horizontal and vertical graphs represent high and low resistance respectively, and the rest lie in between. Devices characterized at various DC test voltages, that is, employing a steady state or time invariant signal, extracts the resistance value, and it is a measure of the resistance offered to the DC current flow. Device characterized with an AC test voltage, that is, with time-dependent or time-varying input signal, extracts the impedance parameter. This test includes device parameters like resistance, reactance, and signal frequency and represents the opposition offered to an AC or dynamic signal current flow. In subsequent slides, we will discuss the graphical properties of VI graphs that provide insight of the device parameters and its behavior. In a semiconductor device, current flow directivity refers to the direction in which the electric current flows through the device. The current flow is determined by the device structure and the forward or reverse biasing conditions. Device that conducts in one direction is called unidirectional, and if conducts in both the directions it is called a bidirectional device. Symmetry and conduction of a semiconductor device refers to the device behavior in forward and reverse bias conduction that is in opposite directions. The device should have identical conduction characteristics in both the biasing conditions. A bidirectional device exhibiting identical conduction characteristics in both the direction is called symmetrical, otherwise they are called asymmetrical devices. Most of the semiconductor devices are asymmetrical, and this property is extensively used in many applications. VI graph shown in the figure exhibits linear voltage-current relationship. For example, devices like resistors, capacitor, inductors, etc. exhibit a constant slope characteristics and are called linear devices. Whereas, most of the semiconductor devices have voltage-dependent resistance characteristics, hence exhibit nonlinear VI relationship and are known as nonlinear devices. In a semiconductor device, positive resistance refers to the property of the device where the current through the device increases with an increase in voltage. This property is common to most of the semiconductor devices. In contrast, negative resistance refers to the property of a semiconductor device where the current through the device decreases with an increase in voltage. This behavior is not very common and is observed in specialized devices like tunnel diodes and gun diodes. The resistance of these devices is also sensitive to the temperature. Figure shows VI graphs of opposite slopes. A positive slope device undergoes Joule heating and acts as dissipative element. On the contrary, a negative slope device can be used as an energy source. A circuit designer using semiconductor devices and energy sources implements and realize various functionalities. In subsequent slides we will study parameters of sources and devices and through their VI characteristics study their suitability for different applications. An electrochemical cell is a popular source of DC voltage, and alternatively DC can also be derived from AC mains supply. A practical voltage source as defined by Thevenin's theorem is made up of an ideal voltage source connected in series with its internal impedance, which limits the load current and also leads to voltage regulation issue. A voltage source connected in series with transistorized common base regulator increases the internal impedance and creates a constant current source. A practical current source as defined by Norton's theorem uses an ideal current source connected in parallel with its output internal admittance, which limits the maximum load voltage and also leads to current regulation issue. In electrical engineering, electromechanical and solid-state switches are extensively used in logic design and power control applications. Figure shows electromechanical or a solid-state switch, VI characteristics. From it we observe that the on and off switching states creates unidirectional and asymmetrical characteristics. Solid-state switches have superior characteristics like low wear and tear, high speed, low contact resistance, low noise, longer life, etc. Diode VI graph exhibits low impedance in forward bias and a high impedance in reverse bias. Further increase of reverse bias leads to a device reverse breakdown and enters into low impedance region. A diode is used in forward low impedance and in reverse high impedance, that is without entering into reverse breakdown region. This asymmetrical property makes it suitable for rectification, switching, signal detection, etc. A diode operated in reverse breakdown region exhibits low impedance and maintains fairly constant voltage for wide-ranging current variations. These diodes, known as Zener or avalanche diodes, are operated in reverse breakdown region, offer low impedance and maintain constant terminal voltage, hence are popularly used as constant voltage regulator. A silicon-controlled rectifier operated in third quadrant exhibits reverse bias diode characteristics. As shown in figure, an SCR in first quadrant operates in various regions, like in A exhibits high impedance, in B and D regions offers low impedance and negative resistance, in the transition C region. SCR, which has negative resistance characteristics, is most suitable for efficient power control and switching application. A BJT or a MOSFET can be operated in various regions. When operated in current saturation regions exhibits high output impedance and hence acts as a constant current source. This characteristic makes it most suitable for a constant current source application. Figure shows a typical datasheet presenting various other graphical parameters as VI characteristics. Hope this video has been helpful in understanding semiconductor device parameters and applications through their graphical VI characteristics. Thanks for your time and hope to meet you in the upcoming video. Bye.